In quantum mechanics, wave function is quite commonly solution of what is called Schrodinger equation. And to understand Schrodinger equation and to understand what is called orbital angular momentum and some other results, a very convenient first step could be to understand the result which is often stated as that momentum is minus attached by d by dx. Now, in proper terminology, the full statement is that when momentum operates on a wave function, it operates as a derivative. So this is a result which is introduced in this lecture first by showing this for a plane wave, which means plane wave means a particular kind of wave function, and I have to tell you what that particular kind is, and then I have to give arguments that the result is not limited to that particular kind of wave function, but that is valid for any wave function. So generalization is the second part. So I have described two parts, and now I start with the first part. The first part is that what is operator. Momentum is a special case. We come to that later. But first, generally, just revise what is the definition of an operator. Which, you know, the overall topic is that we have to choose operator as momentum, and we have to say operator becomes a derivative. But these are special cases. First, to start with general. And in general, there's one generality is that, I said that momentum operates on wave function, but generally wave function, any wave function, position wave function or momentum wave function or any wave function is related to what is called wave vector. So we start with a general thing. Operator's definition is for any operator that it operates on a vector, ket vector, and gives another ket vector. That's there. Now when you represent it, it becomes an alternative terminology to all this could be that if you have a thing and when you throw light from here, then it becomes its shadow. That's the word becomes is one way of remembering. Now this is maybe you can say analogy, and what I first want to say in proper terminology, actual thing, not analogy, actual, and actual what I'm first, my first target is that when you specialize to, becoming means specialized your representation. When you represent a vector by a linear combination of countable or discrete basis vectors. Ordinary example is that ordinary vector you write as a linear combination of I unit vector and j unit vector and so on. So if your basis vector are countable, your basis is discrete, and this column, in that case a vector becomes x component, y component. These you can put in a column. So ket is represented by a column. By sound, this is simple to memorize that result, hopefully. So ket becomes column, another ket also becomes column, and operator becomes, you think of that, between two columns could be what? The answer is matrix. So one way operator becomes, or another terminology is an operator is represented by, and all this and that's one way is matrix. But that is just for completeness, I've said it, but our target in this lecture is not matrix, but our target is a derivative, minus iota h bar d by dx. Now derivative is the other representation. That means the operator can become a derivative. When operator can become derivative? When? That's the question. And the answer is that when operator acts on not column but acts on a function. And in quantum mechanics we mean wave function. operator becomes, the operator is represented by a derivative when it operates on a wave function. And this is so essential that I better revise it before proceeding further. There is nothing new, it's just a revision of what I said in the previous slide. And that is the general result is this: when you specialize to discrete, that I did in the previous slide, and now I say we specialize to continuous. In discrete, this becomes a column, cat becomes a column, and in continuous, it becomes a function or wave function if you want to use it for quantum mechanics. The result is also specialized in the same way, function, and between two functions can be what? A derivative. So that's another becoming another representation of operator. Previous slide I said matrix, and now I said derivative. And that is our actual topic in this course, because we are after a derivative. So now, when you say we are after what I meant in this lecture, and in this lecture our actual topic is not arbitrary operator but only momentum operator. Now, quantum mechanically, operation is like a measurement. So I write a sentence and you try to translate that to mathematics. The sentence is in English. The sentence is the following: that if you measure the momentum of a plane wave, and for those of you who need, I revise what's the definition of a plane wave. Now, the definition is that a plane wave is a wave which has a fixed wavelength. It's the same everywhere it goes, it has the same wavelength, and same wavelength means same wave number. And according to de Broglie expression, that is related to momentum, and the relation is well known. And when you operate, when you measure momentum, it's a plane wave, it had a momentum p, and we measure it will remain a plane wave. Its momentum will remain fixed as before, and that means it will remain a plane wave. Now that's a sentence of English. Now you translate to mathematics. Now mathematics, this partial is actually, you see how much percentage. Plane wave I have translated to mathematics. I have, in plane wave I have written its formula, expression. So that translated. The result of measurement as momentum, that is translated. So three things are translated. One, I say partial because the word measurement is still measurement. Now at that time you think of that, what can be here which retains exponential as exponential. So that does not change exponential. What can be the operator? And the answer is derivative. Exponential remains exponential. And the details of calculations are that exponential remains exponential, but it is multiplied with the derivative of power. So because it's with respect to x, only first term will be differentiated, and differentiation will give x as 1, and you will get iota k. And you because our target is h bar k, so to get that iota k, you have it and you multiply with minus iota multiply with minus iota become 1, and the k h bar is h bar k, and the Broglie expression says that h bar k is momentum. So result of measurement we have seen, or immediately you can say right hand side we have seen, left hand side. Our translation to mathematics was incomplete, and now it is complete. Now it's something definite. It's a derivative. So in a way the announced result is achieved. If we are measuring momentum, then momentum is minus iota by d by dx. The only thing you have to think of is that all over? That means, have we proved that momentum is always minus out of d by dx h bar? Always mean for any wave function, but you should realize, if you have not realized yourself so far, that our target is to prove for any wave function, but we have not proven for any wave function. We have proven only for one particular case, not for all cases. So that is why the lecture is not over. But those of you who want to see only result, they can stop here. The result is, I've shown you the origin of the result. The result is right, but those who want a standard, they should wait, they should complete this lecture, because the proof is not completed. Because we have proved it for plane wave so far, but we have to prove it for any wave function. So that thing remains. And that is the next 3 slides. So that's the next second half of the portion, which is needed for standard, that needed as well. For result, that is sufficient. So now to get standard, I keep proceeding. And the first step is that you generalize it. You know, our target has been generalization, because one way of saying is that we prove the result only for a plane wave, and now we have to generalize it to any wave function. So the first generalization we need is this word any. It's not only plane wave. That's one generalization. But when you have to generalize, you fully generalize it. You make 2 other generalization as well. And that's how you give the proof. So the other generalization, I said 2 more generalization. The one of them is that in place of 1 dimension, you generalize to 3 dimension. And the other generalization is that in place of position wave function, you should be able to say for any wave function, it may be momentum wave function, it may be position wave function, or any wave function. Now, any possible wave function is related to a state. So when you say state, that's our generalization. But mathematically, the state means state vector. So now just what I've spoken, I write. State is state vector, that's generalization. Momentum 1 dimension is generalized to 3 dimension. Now that's equation. That's English is translated to mathematics. Now, what is that? How many quantities that equation introduces? And if you think that, it has 3 quantities, P, they are all, you have to be very careful. And they are all spoken as P, but you have to see one is a hat on it, one is not hat on it, and one is a cat. One is not hat, that's the simplest to understand. That's the classical momentum, Px, Py, Pz, which is even mass into velocity, numerically same as, is nothing new. Now you may think that this is new, blue cat, but actually it is not new if you try to slightly recall what we have already spoken in this or maybe previous lecture. Or if you have not seen previous lecture, then don't worry. You can understand, even if it is new for result, you can understand it. That for, if you like to revise, I can start with the ordinary vector. If you have an ordinary vector and you multiply with I unit vector, you becomes Vx, component. In direct notation, it is that if you have a state vector, you take a bracket, dot product is bracket in direct notation. With position bra, you get position component. You can say component, but what I mean is position wave function. So hopefully either you have read it or it's not surprising to you. It's plausible at least, even if it is new to you, that result. And that result is used 3 or 4 times in, so try to remember that result. And one way of using that is that in place of psi, we specialize with P. P is momentum. So this means left hand side psi is specialized to P. That means the specialization is that we don't have any arbitrary state, but we have a special state which is labeled by, characterized by a fixed momentum. That's one left hand side, and right hand side psi is also replaced with P. Understand when PR means? Psi R means any wave function, and PR means that wave function which is characterized by fixed P, and position wave function which is characterized by, because R is here, that's why position wave vector. So you know what is that? Position wave function of fixed P, one wavelength, one momentum, the boy says means one wavelength. And what is that? That's a plane wave. And the expression for plane wave, which I showed in previous slide, that is minus iota t, because we have to eventually differentiate respect to position only. So minus iota t is not needed and space is less, so I don't show that. So you had kx in 3 dimension become k dot r, and you have 2 pi under root, and 3 dimension become 2 pi 3 by 2. And the Boy relation says that this becomes p, wave number is related to momentum. So I think what I mean to say is that in this equation 1, this blue should not be new to you. If you recall what you have already known, or what is simply plausible, you know p cat as well. You knew that p number, p ordinary vector, even before quantum mechanics. So what is new introduced in equation 1? And the answer is, what I am highlighting is p hat, which is momentum operator. And remember, now we have generalized in every sense of the word. So this is momentum operator general. It can operate on any wave function in 3 dimension etc. So now we have a general definition of momentum operator. Now we have to specialize to, our eventual target is derivative. That means we have to specialize to, that is specialized to derivative. Then wave vector is specialized to wave function. Now I do that specialization, and that specialization will give you the required derivative or required justification. The details is the following: that when you specialize to position, okay, maybe I start with here. That's familiar to you, more familiar to you. In 1 dimension, for a plane wave, we said, at least I introduced that momentum becomes, that means momentum is represented by minus by d by df. And our target is that, is it only for a plane wave or it's for any wave function? Psi x is any. And the answer is it's valid for any wave function. Another generalization is that wave function can be even in 3 dimension. That means rather than x, we can have a r which has x, y, z, all. So this is the result, and in that case you can say that momentum operator becomes the derivative, and that is the announced topic of this lecture. Now detail, if you are interested, you have to pay attention to a step by step. If you stay with me, then I have these details to get start from left hand side. What I do is that I have to replace momentum operator with right hand side has no momentum operator. Right hand is only numbers or variables numbers. So how can I replace p operator with a number? And the answer is that to get the first result of the previous slide, that we have to operate momentum operator on momentum state. So that means we have to operate p on p cat. How can we justify? That's a question. And the answer is that you can say that p is multiplied with identity operator. The identity operator you can write any time. For example, for odd number you can write 4. You can write 4 as 4 multiplied with 1. Looks trivial. But there is a theorem which says the trivial result is not that trivial, that can give you useful results as well, and that theorem is called completeness. That means identity operator is equal to completeness, and the completeness, maybe I have been writing this as a sum, but if our labels of state is continuous, the momentum is continuous, then sum becomes integral. So that is the completeness theorem. Now why I have brought it here, this question answer I have already spoken. That means I have brought it here so that P operate anyway, but while I am speaking I show you. I brought it here because if P operator, which is something new to us, if that operates on P state, then the result is not new to us. The result is ordinary three-dimensional vector. It's not a state vector, it's ordinary vector, classical vector, which is equal to mass into velocity, which has px, py, pz. So we have replaced it by a familiar thing. Now what is the use of that? To get further usage, what you do is a bra and there's a cat. You bring them together. And remember RP, you recognize what it is. That's the second result I showed in the previous slide. In the previous slide I said R psi psi R, RP is PR, and PR means a wave function with fixed momentum. That's the plane wave. And the expression for plane wave is exponential. So that is the introducing this formula. Now I have recolored P to in anticipation for the next step, black to red. Okay, in the next step, here rather than proceeding forward, I think in my opinion for these three steps, I think it will be easier for students if you proceed backward. I've shown you result. You can prove that this is equal to that and then this is equal to that. So what you have to do yourself, it's a simple thing you can do yourself. Take a pause to that, stop that video, and meanwhile you take a pen and paper and you replace del. You should know the del is x derivative into I unit vector, or in American terminology x derivative into x unit vector, and then y derivative into j or y unit vector, and z derivative into k or z unit vector. When you say x derivative, you operate on power px, it gives you px. When you take y, it will give you py. When you z, it's pz. All in all, px, py, pz. Linear combination is px, is momentum, and that is there. So take your time in proving it, and now you just see what we have obtained. Now, as it were, you again go forward. Then one thing is that because it's integration is back to momentum and differentiation is back to position, they are independent. You can take it outside, which means rather than first differentiation and then integration, you first integrate with respect to momentum and then differentiate. You see what the result is. And meanwhile I have done another thing as well. I have gone back here as well. This I replace with this thing which is that. Now I introduce green color. Rest of it you make sure you understand this is there. This is all the way it's here. Only that thing is new. And hopefully you recognize this combination. This has appeared many times. I already even this combination used it here. You remember this? This is identity. Now here it is actually we are forward and then we are taking backward, and all in hopefully whatever you take your time in understanding, and And the result is that this becomes identity, and identity is like multiply with 1 is nothing, and what you are left with this, and that is our right hand side. So that's it for this. So we have proved that momentum becomes minus v by del. So should I stop? And the answer is almost right, but not quite, because in conclusion, I want you memorize this result. And in memorization, so far, sorry, when I said memorize this result, that means you memorize the general result which is valid for anything in cat, anything in bra. Now, in this slide, we are limited. The operator we have anything. It can, okay, no, sorry. It's momentum operator, but in cat we can have anything. In bra we have limited only R. Now, before concluding, I have to generalize this bra to arbitrary bra as well, and that I do, and then I write the result and finish, and that is achieved in the next slide with conclusions. And what happens to the bra? You have to, if you have studied, recall. If you have not studied, just recall your much earlier thing in education, and that is that A dot B in ordinary is AX BX plus A by BY. In direct notation, that is dot product is bra cat, and this summation is not necessarily to our X or Y. It can be over any 1, 2, 3, 4, 5, 6, any, not only X and Y. And you know, as I said, the main topic is what happens to the bra, and the answer is that bra components are complex conjugated. And in continuum, if your independent variable is not discrete I, but it's continuous, maybe R position, then summation also become continuous, namely derivative. Sorry, integrate. Now you do something specialization, and that specialization is that now we apply to quantum mechanics. That in cat, any mathematics we specialize to eta. Now what is eta? Eta I have given name to psi into p, momentum. Now if that is there, then what is the dot product of eta with R? And that is, you know, the result I showed you for psi. Psi R is psi R, eta R is eta R. Now for the next step, you just write the definition of eta, so you get that. Hopefully you have seen it, you understand it, because that's just substituting definition. And now that is the result in Brown, and that is the result we spent the whole previous slide for that. So the next step is that you take this combination and you recognize what it is. And this much is what I've given name eta. And that result I've rewritten here, nothing new. And in place of eta R, I've written that. That is nothing new. So that becomes the result which you have to better memorize it. And the result I write it again. And while writing it again, you know, I take you to maybe keep you concentrating on the relevant things. So middle steps you need not memorize. You have to memorize left hand side, which is here, and right hand side. And right hand side I've done a slight reordering. This round bracket I've taken it here, and I've introduced colors, because different colors mean different things. And how many colors you have? Think of that. Anyway, what I mean is 4. One color is that momentum operator becomes derivative, and that is the announced topic of this lecture. In a way, the target is achieved, but with that there are 3, you can say side result, but actually they are to become very important in their own right. So better pay attention to these as well. And these are, first you sense orange. In orange, what it is? That cat becomes wave function. And whatever is in bra, and that was the only thing in this slide. Previously we had R, and now we have said it can be any. If any, then you have to have complex conjugation of that. With R, I didn't need. R is real, so you didn't need complex conjugation. But if you have arbitrary, then you need complex conjugation. That means the bra becomes complex conjugate wave function, and I've deliberately replaced the letter phi with the psi, because you should be mentally flexible. It's not necessarily phi. There's nothing special to letter. It can, whatever it is, you call it phi, you call it psi, whatever it is. What is in the result is that what is in phi, what is in bra becomes a complex conjugated function, which in quantum mechanics is called commonly is wave function. So which color remains? Think of that. Only yellow. And yellow is what? That bracket becomes integral. So that's it. You know, the picture I've shown previously as well. Although previously I had written it for 1 dimension, now we're to 3 dimension. You understand what picture is here for? And that is that if you have a general thing, it becomes, or it represented by matrix, but our target, if the general thing is momentum, then the thing which I did in the maybe most of the previous slide is that it's not only it's not matrix, it's a derivative. That derivative means we specialize to position wave function, and when you specialize to position wave function, it becomes the announced derivative. Announced was d by dx, and in 3 dimension it's del. So it becomes momentum. Generally thing in this special case it becomes a derivative. That's all the topic of this lecture, and this lecture is over now, complete.